So I'm starting with today's discussion. So we talked about drag force, and these are series of experiments that will first baffle you, and then you will get to understand why this is happening. I've already given some hint regarding these yesterday also. So this is what I was talking about as open wind tunnel. Open wind tunnel, that is, this is a wind tunnel, and this is the chamber in which there is pressurized air. So air is coming from below, and this is the object which you want to test for drag force. That is, air will be blowing in upward direction. It will push this object depending on how the surface is, what the shape of the surface is. This deflection will actually be calibrated, that what force is it exerting on this object. So the force it is exerting on the object is essentially the drag force. So the observation was somewhat like this, that when the wind blows over this roughened ball, so this is a roughened ball, that is, you have created surface roughness by a sandpaper or something like that on a ball, and you have kept it above the wind tunnel. This is open wind tunnel. You can think about this as a jet of air that is moving up. So what you see is, as the speed increases, the drag force also increases with the speed. After a certain speed is reached, the drag force does not further increase. Instead, it starts to decrease with a fluctuation. And then again, it starts to increase. So can you think about it, why this is happening? Why there is not a uniform trend? Why there is this transition and these two different kind of slopes of the graphs? Hani, Rajesh.
सर वो ऐसा कुछ जो कॉन्सेप्ट हमने पढ़ा था टर्मिनल वेलोसिटी जैसा, जहां तक मुझे लगता है उसकी वजह से मे बी होगा, वंस इट रीचेस द स्टेडी स्टेट कंडीशन तब ड्रैग फोर्सेस का उस पे वेरिएशन कम हो जाएगा टाइप्स मे बी।
व्हाट डू यू मीन बाय स्टेडी स्टेट?
नहीं, स्टेडी स्टेट मतलब सर, मतलब वो जब नीचे नीचे आ रहा है तो विस्कस तब लगना शुरू हो रहा है, तो ऐसा एक पॉइंट आ जाएगा जहां पे अब वो ज्यादा एक्सेलरेशन नहीं कर पाएगा अपनी, तो इट इज लाइक टेंडिंग टू सम मतलब बीच की वेलोसिटी जहां वो रुक मतलब
ओके,
मतलब यस सर वैसा कुछ।
okay, I will explain this in a moment. Any other inputs, Naveen?
Yes, sir.
What do you think?
सर ड्रैग कम लगने का वजह से स्ट्रीमलाइन समथिंग से होगा।
My question is, had this curve been like this, for instance, this is drag force, this is speed, the curve would have been like this, we wouldn't have asked you this question, because this is a behavior. But in this behavior, this is not behaving in a normal sense. Up till one speed it is increasing, then there is decrease with certain fluctuation, and then again it starts to increase, but now with at a lower rate. So keep this experiment at the back end of your mind. We will come to it at the end of the lecture. I am now showing you second experiment. These are now two open wind tunnels. So in both the wind tunnels, air is blowing up. Now I am not measuring the drag force, but now what I will do is I will put two different objects here and then try to see which object has more drag. So in this case, for instance, I have kept the roughened ball here and a smooth ball here. When the air is not blowing, you know that this balance will be a horizontal line. Now if I start to increase the speed, what do you think? In which direction will the balance lean? This is the smooth ball of same diameter. This is the roughened ball of the same diameter. Both are at the same height initially when the air is not there. I simply switch on the wind tunnel so that air starts blowing and I have some speed. What do you think? In which case drag force will be higher? Smooth ball or roughened ball at low speeds?
सर ड्रैग फोर्स सर रफ बॉल में ज्यादा होगी.
So roughened ball will be higher than smooth ball at
low speed.
low speed. It means balance will be in which direction? It will be, so what will happen is this will be pushed up and this will lean like this.
Yes, sir.
Now if I keep on increasing the speed, say at high speed, what will happen? Suddenly there will be reversal of this line. It will
सर
be
टर्बुलेंस क्रिएट होगा ना रफ बॉल में फिर.
So at high speeds, drag force of smooth ball is greater than
रफ बॉल.
roughened ball. So you have given a hint that due to turbulence.
सर समझ गया सर. जो पहला केस था उसमें भी टर्बुलेंस प्रोड्यूस हो रहा होगा.
किसमें?
इस वाले केस में.
हाँ, इस वाले केस में भी I am again giving you a hint. This was actually the laminar region. This was the
transition region
and this was the turbulent region. And in the second experiment also,
सर एक तरीके से सर वैसा है ना स्विंग का कॉन्सेप्ट जो होता है बॉल में, क्रिकेट बॉल में वैसा ही होगा ना यहाँ पे.
क्रिकेट
ऊपर वाला केस था सर. क्रिकेट बॉल में जो स्विंग होती है बॉल, एक तरफ वो लैमिनार होता है फ्लो, एक तरफ टर्बुलेंट फ्लो होता है.
हाँ,
उसके वजह से वो बॉल स्विंग करती है. तो वही कॉन्सेप्ट यहाँ पे भी लग रहा है ना.
okay,
ऊपर
so
वाले
that is what you are talking about is I think you are talking about Magnus effect.
जी सर.
So Magnus effect is little bit different, but it involves the same drag and lift forces. So that is something that if some ball is spinning, it will have some non-zero lift. जैसे अगर बॉल ऐसे है, ball is stationary, it is symmetric object. In the flow, it will have zero lift. Although it may have non-zero drag, but it will have zero lift because this is symmetric. But if the ball itself is rotating, then it will have non-zero lift. And that was observed by scientist Magnus, and that is called Magnus effect. The magnitude of this was actually found by two scientists. One was called, that is called Kutta-Jaworski theorem. We will not go into detail of that. These were German and Russian scientists who quantified the magnitude of this lift force. And Magnus was the person who actually physically saw this effect. So that is a little bit different, but it is on similar lines. So I'm coming back to the two experiments. So this was a roughened ball, this is the smooth ball. And we have observed that at low speeds, the smooth ball will have lesser drag, whereas at high speeds, the roughened ball will have low drag. Now this was about the two balls. I have the third experiment. In this case, I have a smooth ball here and I have a streamlined shape here. Now I keep on increasing the speed. What do you think, in which case the drag force will be higher, and will it change at some speed or it will remain the same trend?
Drag force would be higher for the sphere, वो तो streamlined है दूसरा.
So drag
और यहाँ
force in
would be
the
higher for
smooth sphere should be always greater than drag force
streamlined.
on streamlined body.
Only to the condition अगर viscous fluid ना है तो.
This is in air.
This is in air, no? Yes, sir.
So this is actually at
Low
Reynolds number.
low number, yes, sir.
So Reynolds number is rho Vd by mu. So low Reynolds number means either mu could be small. So in this case, Reynolds number is low due to mu being small because it is air. So these are certain observations, and there's another observation which we have talked about earlier also, that if this experiment was carried out in a highly viscous oil, then we know that this blunt body will actually reach the bottom surface first. That is, drag force in the streamlined body will be higher than in this sphere. So this was at low Reynolds number.
High.
What are you saying?
Viscous
Sorry.
fluid में तो.
No, I think did something wrong here. This
yes,
should be at
high Reynolds
number, and this should be at low Reynolds.
Low.
So this situation was at high Reynolds number because mu was small, so Reynolds number was high, and this was situation at low Reynolds number. So we saw that at low Reynolds number, streamlining has adverse effect, whereas at high Reynolds number, streamlining has an advantage. So why do you think so is the case? Why do you think is the case? And one thing more, we observe that a roughened body has higher, or a roughened body has a lesser drag as compared to a smooth body at high Reynolds number, whereas the opposite happens at low Reynolds number, or say low speed. So these are certain observations. We will come to it with the reasoning why it is happening so. So this is the case which I have just discussed. So this was the ball, this was the streamlined object. We know that this ball will reach first, this will reach afterwards. So this will have a greater terminal velocity. Now, I have another set of experiments now. Say, I have wind blowing over these different shaped bodies. Say the air speed is 200 miles per hour. What do you think will be, in which case you will have the highest drag force?
So case 1.
Highest drag force.
Sir, in the rectangular region.
So I am giving you a hint.
Aero.
This diameter is equal to the maximum, this diameter. And this is very much small as compared to this. Okay. Now try to think.
Sir,
What is the difference between these two? These are same bodies but kept in opposite orientation.
सेकंड वाले में आएगा शायद.
सर फर्स्ट वाले में सर. मतलब
फर्स्ट वाले में. So this is the answer.
First, okay.
If it is 1 unit drag force in this case, you have 9.3 units drag force in a cylinder, and you have 4 times the drag force as compared to aerofoil in the case of a rectangular object of very less cross-sectional area as compared to this.
Spherical, sir, 9.3 कैसे?
This is not spherical, this is say a cylinder.
अच्छा.
So what is happening is, so these are also the 2 dimensions. So this aerofoil may be like this, and this rectangle may be also like this. So these are just the front views of the objects. So you have kept this in on the wind tunnel, and you saw that through experiments, if the wind speed is constant, you saw that the drag force is highest in case of a cylinder as compared to that of an aerofoil. And ironically, this is the case. If this is say diameter D, and if I take a wire of diameter D by 10, both of them have the same drag force. So that is the power of this particular shape. And why it is so, we will get to know just in a moment. So this also tells you something, that it is something counterintuitive. As per your intuition, you could predict less drag in this because this is a very small cross-section area. And as per our intuition, हाँ जी बताइए.
सर ये सारा ये ड्रैग फोर्स इसको हम एरिया के बेसिस पे कंपेयर कर रहे हैं ना?
एरिया के बेसिस पे नहीं, शेप की बेसिस पे.
मतलब क्रॉस सेक्शनल एरिया, मतलब क्रॉस सेक्शन किस शेप का है उससे डिपेंड कर रहा है ना एक ड्रैग फोर्स.
ये क्रॉस सेक्शन किस शेप का है. जैसे ये एरोफॉयल है, ये भी एरोफॉयल है, सिर्फ 180 डिग्रीज पे टिल्टेड है. ये एक रेक्टेंगुलर बार है, ये एक सिलिंड्रिकल बार है. ये सिलिंड्रिकल बार का डायमीटर इसके मैक्सिमम डायमीटर के बराबर है. इसका जो ये एरिया देख रहे हो ये बहुत ही छोटा है. बहुत छोटा होने के बावजूद इसमें ड्रैग फोर्स 4 टाइम्स है एरोफॉइल के कंपैरेटिव. So that's why we have moved from, you might have seen the aeroplane of Wright brothers. It had a number of wires and rods of circular cross-section area, and that's why that had a large amount of drag force. So we are able to see, if we have the same diameter cylinder, it has around 9.3 times drag force as compared to
drag force के वजह से सर ये था, वो इसलिए फेल हुआ ना कि ज्यादा वेट नहीं उठा पाता.
वेट तो उठाना इसलिए नहीं है, ड्रैग फोर्स ही बहुत ज्यादा है.
उड़ तो गया था तब भी.
नहीं उड़ तो गया, वो फिर उसमें पावर उतनी ज्यादा लगेगी ड्रैग फोर्स को ओवरकम करने के लिए. अब जैसे एम्बेसडर भी तो चलती थी गाड़ी, एम्बेसडर या जो पहली गाड़ियां थी, they were also running, but they had much more power input because there was lot of drag force that you need to overcome to make the vehicle to accelerate or move with constant velocity. तो इसमें ऐसा नहीं है कि ये नहीं चलेगा, ये चलेगा, लेकिन इसमें और पावरफुल इंजन चाहिए होगा उतनी स्पीड तक पहुंचने के लिए as compared to.
तो सर मतलब हमें डिजाइन ऐसे करना होता है कि ड्रैग फोर्स कम से कम लगे.
ड्रैग फोर्स कम से कम लगे, तभी आप देखते हो कि जो साइक्लिस्ट होते हैं उनका जो हेलमेट होता है वो भी स्ट्रीमलाइन शेप में होता है. फिर जो फिशेज हैं, you have already seen fishes are of streamline shape. So it means if this is of streamline shape, what do you think? They are moving with high Reynolds number or low Reynolds number, fishes?
Low Reynolds number, high.
High. Had
Yes,
it been low Reynolds number, then they will not be streamlined.
Will not be streamlined. Yes.
Then you can think about it. That's why bacteria and viruses, they are not streamlined objects, because they are, आपको याद होगा creep flow approximation, you remember? It is highly viscous region of flow. If a bacteria or a virus enters our cell, viscosity is too high, that is Reynolds number is too low. So अगर वो बैक्टीरिया या वायरस स्ट्रीमलाइन होते तो वो तो बिल्कुल ही मूव ना कर पाते, उनमें और ड्रैग फोर्स हो जाती. Is that clear?
Yes, sir.
So nature has evolved in such a manner to minimize work. Is that clear?
Yes.
सर
हाँ जी बताइए.
सर एयरप्लेन का कॉन्सेप्ट तो उससे है ना, बर्ड से आया था ना.
नहीं, बर्ड से तो देखो वो विंग्स का होगा. अब जो उसकी बॉडी है, व्हाई इट इज ऑफ दिस शेप. एक ट्राउट फिश होती है, ट्राउट फिश. It is exactly the shape of an aerofoil. Now it is also debatable whether we got it from fish or we got it from some bird, and some might also claim that it was our own imagination, and that is essentially incorrect. We are copycats in reality. We always copy nature.
जो विंग्स हैं,
हाँ जी क्या कह रहे हैं, क्या कह
सर
रहे
जो
हैं आप?
विंग्स हैं, विंग्स एयरप्लेन के.
हाँ विंग्स नहीं, विंग्स भी तो एरोफॉइल शेप ही होती हैं. तो अभी जो
बट
रिसर्च
एक
चल रही है,
देखा था
जैसे
मैंने
हम कह
वीडियोस
रहे
में,
हैं,
आउल एक था जब उड़ रहा था, वो
हाँ.
हीलियम गैस समथिंग से मतलब पास कर रहा था. ऐसा था कि फिजिबल था.
हाँ.
तो उसके एंड्स पे सर वो जो फ्लो था सर, एक वॉटिस फ्लो टाइप बन रहा था वहां पे.
हाँ, आई गॉट यू.
वो
यू आर सेइंग कि जो उसके विंग्स भी होंगे उसका भी क्रॉस सेक्शन कुछ ऐसे होगा.
यस सर.
So that is true, but it is debatable that what was the first motivation behind aeroplane. There might be many motivations. Somebody might have watched a bird fly, somebody something else. So that is debatable. You cannot claim anything as such. But what is true is we have got inspired from nature only, nothing more than that. So aerofoil has very less drag. Now let me know, there's a follow-up question. If an object is perfectly streamlined at high Reynolds number, what will be the pressure drag? It will be nearly
0. Yes.
So please remember, the very definition of streamlined body is a body which at high Reynolds number has nearly 0 pressure drag. So you should always define streamlined body as a body which at high Reynolds number has nearly 0 pressure drag. That is the definition of the streamlined body. So going from blunt body to streamlined body, we are essentially reducing the pressure drag. And why I have imposed the condition of high Reynolds number? Can you think about it? Why?
सर क्योंकि उससे हमारा कोफिशिएंट
में भी जाएगा तो फिर बेयर कर पाएगा.
लो हो जाएगा.
क्या कह रहे हो? Why do you think so? Why I have written down high Reynolds number?
सर विस्कस फोर्स कम लगेगी ऑब्जेक्ट पे.
Okay. So now I'm explaining you the fact. Say these are streamlines and you are able to see this white region. So this is the boundary layer region. So as the fluid is flowing, you know that velocity at this point will be what? 0. And this is called the
stagnation point.
Stagnation point. So first of all, let me explain it with the idealization that there is no viscous effects. मान लीजिए इनविसिड रीजन होता तो यहाँ पे और यहाँ पे प्रेशर कितना होता? हाईएस्ट. यहाँ भी हाईएस्ट होता और वेलोसिटी कितनी होती? 0 दोनों केसेस में. तो इसका मतलब क्या हुआ? अगर यहाँ पे वो u इंफिनिटी था और फिर यहाँ पे 0 हो गया, फिर यहाँ पे u इंफिनिटी हो गया, इसका मतलब क्या हो रहा होगा फ्लो के साथ? यहाँ पे वेलोसिटी 0 है, इसका मतलब
बैक
यहाँ
फ्लो हो
से
रहा है
यहाँ तक इसको क्या करना चाहिए? एक्सेलरेट, और उसके बाद क्या करना चाहिए?
सर बैक फ्लो होने लगेगा ना सर?
हाँ, ब्लैक फ्लो नहीं होता, मैं वही बता रहा हूँ क्यों नहीं होता, डिसेलरेट
हेलो
होना चाहिए। And is that clear? If pressure here is say P1 and pressure here is P2, you know that P1 is equal to P2 in case of inviscid region. If I don't assume any kind of viscosity, this is the result of Euler equation. I will come to the fact that when we add the viscous effects, it will not change much, but it will change something. So P1 is equal to P2 and these are the highest pressures. यहाँ तक clear है? यहाँ तक clear है? Now, as these are highest pressures and we know that V1 is equal to V2 is equal to 0. So velocities are 0 here. So what does that tell you? That velocities will accelerate because it is 0. If the fluid is to flow past this, then it should accelerate somehow. It reaches some maximum velocity here at the shoulder and then again starts to decelerate. So this deceleration actually could have resulted in flow reversal. Deceleration का क्या मतलब है? Net
तो
force.
ये तो ऐसे भी सर हो सकता है सर कि थ्रू आउट द सरफेस 0 होगा।
वो कब है? When it is viscid region. हमने आयलर इक्वेशन में क्या देखा था?
अच्छा इनविसिड रीजन के लिए, ठीक है
मैंने
सर।
देखो आयलर लिखा हुआ ना यहाँ पे,
अच्छा अच्छा सर वो नोटिस नहीं किया।
ठीक है, तो ये it will accelerate and then decelerate, and you know that if it is accelerating it means some force is acting in the direction of flow. If it is decelerating it means some force is acting against the flow. And in inviscid region or Euler equation, what are the forces? If you remember, they are only
प्रेशर फोर्स।
pressure forces. It means if I ask you dp by dx is positive or negative in this region?
नेगेटिव सर।
Negative. And what about dp by dx in this region?
पॉजिटिव।
Positive. So which is favorable?
लेफ्ट हैंड साइड।
This is adverse pressure gradient, this is favorable pressure gradient. So due to this adverse pressure gradient, there can be flow reversal, but that does not happen. Why? Why does that not happen? Try to think about now in the real situation also, the pressure force will act in the similar manner. The only effect is the viscous effects will be superimposed in the previous effect. So you know that if I take any fluid element here, due to this no slip condition, it will be subjected to force in this direction due to viscous effects. Ye clear hai? And due to pressure effects also, it will be again pushed in this direction. But what do you know? If the Reynolds number is high, the flow velocities in this region is far less as compared to in this region. So this will tend to move the boundary layer in this direction. And that's why in an aerofoil, in normal conditions, there is no flow reversal. That is viscous effect and pressure, adverse pressure gradient, both are causing the flow to get reversed. But this momentum of the upper layer is keeping the boundary layer adhered to this region. It is not allowing it to make the flow reversal.
सर वही टर्बुलेंस में से इतना उनके पास मोमेंटम होता होगा कि वो सर जो एडवर्स प्रेशर ग्रेडियंट है उसको
So when
overcome
it is high Reynolds number, there is a turbulent boundary layer here. So high momentum and low momentum fluids, they mix with each other and the flow separation is averted. But what happens in the case of blunt? हाँ जी बताइए.
ये boundary layer separation है.
हाँ, but in case of blunt body, what happens is again when the flow here you can see there is flow boundary layer separation. So why it has happened? Because viscous force might be acting in this direction. But now please remember the pressure difference between these 2 points is very large. So the pressure force is also very large. So this flow, although at high Reynolds number, is not able to actually avert the बाउंड्री लेयर सेपरेशन, लेकिन फिर भी एवर्ट कर देगा अगर बहुत ज्यादा स्पीड हो. तो आप देखोगे अगर स्मूथ बॉल है तो यहीं पे फ्लो सेपरेशन होना स्टार्ट हो जाएगा, और अगर रफ एंड बॉल है फ्लो सेपरेशन थोड़ा आगे जाके होना स्टार्ट होगा. एंड दैट्स व्हाई व्हेन यू इंक्रीज द वेलोसिटी this flow separation has actually got delayed, and this has low drag at high Reynolds number. इस केस में वेग फॉर्मेशन ज्यादा हो गई स्मूथ बॉडी के केस में, और इस केस में वेग फॉर्मेशन कम हो गई. So that's why pressure drag in case of roughened body is far low at high Reynolds number as compared to the smooth body. हाँ जी, clear है?
Yes.
So now I am coming to the last part, then I will break. So please remember now, in case of blunt bodies, this is the magnitude of pressure drag, this is the magnitude of the viscous drag. In case of laminar regime, and in case of turbulent flow, this is the magnitude of pressure drag and this is the magnitude of viscous drag. So you are able to see the net drag is less in case of turbulent flows. But when I have streamlined body, in case of streamlined body, the graph will look like somewhat like this. That is, I will have only which drag force will I have only if I have only streamlined body? If you remember, only viscous drag. So that's why if I have streamlined body, I always have low drag in case of laminar regime as compared to the turbulent regime. So please remember, in case of streamlined body, this is the dictating thing, and in case of blunt body, this thing is the dictating thing. And that's why, one last point, have you seen a golf ball? Golf ball has dimples. These dimples are there only because it is a bluff body and we want to make it turbulent. Then only you can have less drag as compared to the laminar regime.
So ये जो grooves बने रहते हैं उसको surface roughness increase करने के लिए बनाए जाते हैं.
हाँ. So it actually brings the ball into a turbulent regime much more faster. Now one last thing, then I will end the meeting today. This is just 1 minute thing. We have talked about laminar flows till date, modeling. This is called Reynolds Average Navier Stokes equation. This equation is different from your normal Navier Stokes equation only in terms of this term. You are able to see. This term is extra as compared to the normal laminar Navier Stokes equation, and these are called Reynolds stresses. So these have come because velocities now are defined as the mean component plus the fluctuation part. You don't have the exact definition of velocities. You always define them in terms of mean and fluctuation. And this is called Reynolds Average Navier Stokes equation. So we will not get into details of this because this is a subject in itself, but you should always remember that as we had Navier Stokes equation for laminar flow regime, we had an corresponding equation that is called Reynolds Average Navier Stokes equation for turbulent flows as well. So that ends your course. So thank you very much for your cooperation, and if you have any doubts, I can clarify those doubts in a doubt session which you can schedule. We can fix up a time if you like. Otherwise, best of luck for your MSTs and your future ahead.
Yes, sir.
Yes, sir.
Sir,
Thank you.
sir, the हमने फ्लूइड तो पढ़ा सर, ये इज दिस फ्लूइड एंड हाइड्रोलिक मशीन्स
नो
कि मतलब क्या है? बिकॉज मैं जब ऑनलाइन पढ़ रहा था सर ड्यू टू समथिंग, तो उसमें अलग चीजें कवर्ड हैं, लाइक आई couldn't find how much detail you have got into, like वो
फ्लूइड
काफी
मशीन्स तो सर 4th ईयर में है ना।
वो फ्लूइड मशीनरी है, दैट इज टर्बाइन्स एंड ऑल दैट स्टफ, पंप. So
Pumps and
that,
yes
turbines.
sir.
so please don't bother about it. You will not, there will be no repetition of the course material. जो fluid machines होगा उसके अंदर you will have different subject matter.
ओके, तो सर मतलब उसमें ऐसा नहीं होगा ना, लाइक ऐसा, ये काफी इंटरेस्टिंग था, मैं तभी इसको पढ़ रहा था, बट आई डिडंट फाइंड एनीवेयर जहाँ पे हम इक्वेशंस में इतनी डिटेल में घुसे थे,
नहीं
so
नहीं,
that's
वो
why.
पता है क्या, you can always, there are three methods, either analytical solution, numerical solution or experimentation. So that fluid machinery part is more or less based on experimentation, little bit of analytical part, but it will involve similar principles, although seemingly they may seem to be different. But Navier-Stokes equation is the actual parent equation, which will actually dictate the fluid flow and all the forces you will study. क्योंकि टरबाइन में भी तो ये आएगा कि क्या फोर्स प्रोपेलर पे लग रही है.
yes sir.
तो टरबाइन के ब्लेड्स भी आपने देखा होगा, दे हैव सम स्पेसिफिक शेप, and that is dictated by these equations only. So you cannot get away with these equations. अगर आप superficially देखना चाहते हैं, then you can neglect these, but these are at the heart of everything you design.
Okay. तो मतलब हमने अभी सिर्फ we have to focus on the equations only right
Equations
now.
and their potential applications. We have already studied the application part also a little bit.
Yes sir.
So that is as it is. So you will actually find rewarding the entire course, because in second year this kind of course is very helpful. This will open up your avenues in the rest of courses also which you study.
Yes sir.
Okay, then best of luck for your MSTs, ESTs, and great future ahead. We will meet somehow in some other course.
Yes sir. सर आपसे मिलने आ जाएंगे सर आपके
कोई इशू नहीं है. We
चैम्बर
will positively meet in the campus. Let's
Yes
hope
sir.
it starts early. Okay, then best of luck to everyone. Okay.
Thank you.
Okay.
Thank you.
Thank you, sir.
Okay, Jai Hind. Okay.
जय हिंद.
Jai Hind, sir.
Jai Hind. Okay.